Now let's see the joint probability distribution. Joint probability distribution. So joint probability distribution, or you can represent it as P of capital X comma capital Y, models probability of co-occurrence of two random variables X comma Y. So if you specifically talk with respect to the computer vision, in computer vision, joint probability distribution is commonly used to model the relationship between two or more random variables. For example, suppose we have two random variables, capital X and capital Y, where capital X represents the intensity of a pixel. Let me put it in writing. So this one we call it as joint probability distribution. So P of capital X comma capital Y. So let's take an example from the computer vision. So let's we have two random variables, capital X and capital Y, where X represents the intensity of a pixel in an image, and y represents the corresponding label corresponding label of the object in the image. So we can use the joint probability distribution to model the probability so this is what now to model the probability that a pixel has a certain intensity and corresponds to a certain object label. So the joint probability distribution of capital X and capital Y is denoted by P of capital X comma capital Y, and is defined as probability the probability that X takes on a certain value of small x, and Y takes on a certain value of small y. So we can represent the following model as P of X is equals to small x, capital Y is equals to small y. Or you can also say probability of capital X is equals to small x, capital Y is equals to small y. So in computer vision, the joint probability distribution can be used for a variety of tasks, such as applications in, I'm specifically worried about computer vision because this exactly fits there. Applications in CV, it can be used a variety of tasks, uh, such as image segmentation, to object recognition, and 3, image classification. So for example, in image segmentation, the goal is to partition an image into regions that correspond to different objects or parts of objects. The joint probability distribution can be used to model the relationship between the pixel intensity and the object labels. This is in image segmentation, which can then be used to segment the image into different regions. Similarly, in recognition and image classification, the joint probability distribution can be used to model the relationship between the features of an image and the corresponding object labels. So this can be done by first computing the joint probability distribution of the image features and object labels using a training data set, and then using this distribution to classify new images. So let's see some of theoretical stuff of the joint probability distribution. For discrete random variable, the joint probability mass function can be represented as P of capital X comma capital Y is like a table that sums to 1. Like this table that sums to 1. Even it seems like, the example that we have taken for the object, I think it's for object segmentation, or image segmentation. For that we have taken example. So in this, the joint probability distribution can be used to model the relationship between pixel intensity. You can find the pixel intensity. Let's consider this as an image and this is as a pixel intensity, and the respective labels of the image. So let's take this as a pixel image and discrete, and P of X comma Y, capital X is capital X is pixel, and then capital Y is classification, obviously discrete. So for discrete random variable, the joint probability mass function can be represented as P of capital X comma capital Y, and it's like a table that sums to 1. And if you do summation of P of capital X is equals to small x comma capital Y is equals to small y, and double summation of x y, then it's equals to 1. It's like, this, you have this pixel, and you add up all together, then what you get is equals to 1. That's what is your joint probability distribution. These are called joint probability distributions for 3 random variables. This is for the 2 random variable. You can have a 3 random variables. For 3 random variables, we will likewise have a cube. Here we have a 2-dimensional one. For 3 random variables, we'll have a cubic. Just put one more dimension here. That's it. We will likewise have a cube for the probability mass function for more than 3 random variables to similar analogy holds. And for 2 continuous random variables, this is for discrete random variables. If you have a continuous random variables, x, capital X and capital Y, we have joint probability density function. Probability density function we can represent as a P of capital X comma Y. So now for this, as you know that for density function, it doesn't make any sense when you calculate the probability for a particular value, because it's a continuous variable. So that's the reason we take up the density of it. We take up the density, we calculate the area of from one point to the other point. We'll go with the intervals. So for that, here in this case we have 2 dimensions, so I have to go for the double integration. As I have 2 dimensions, I have to go for the double integration. Integral of x y, P of capital X is equals to x, and capital Y is equals to y, dx dy. and the overall area of this integration is 1. That's what. I think if you have studied your engineering well, it would be very easy to do the double integrations also. So you will start with the dy, integration with the dy. Once the dy has been completely converted into the dx, only you have to have dx values, and then whatever is there with y variable all should be converted into either constants. Then you will have x into dx. The y1 will be replaced with the limits. Then you will have a single integration of x dx. Then you can do the integration of that also. This is what you do in algebra. Widely you do vector algebra in engineering. Not only that, everywhere you use this. Because of this integration and then derivatives, because of that only most of the mathematical no engineering equations are modeled. Okay, so this is what a joint probability distribution. So the joint probability distribution uh, the joint probability distribution can also be used to compute other important measures such as the marginal probability distribution, the conditional probability distribution, and the covariance between the random variables. These measures can be used to gain a deeper understanding of the relationship between the random variables and to develop more sophisticated computer vision algorithms.